So, hi to all. My name is Alexander Fedorov, and I want to introduce you the Visualize SDK, the new standard for the engineering graphics. And I want to start maybe from the main question. What can be visualized through the Visualize SDK? First of all, it is a 2D drafts data, which is widely used in the many applications, like, for example, computer-aided design applications. Another type of the data is 2D maps. Here it is important to know that this type of the data are very critical from the rendering performance point of view, because usually it contains a huge amount of objects with different attributes, and such situation typically produces a significant number of the GPU calls, which certainly decrease the performance. Another type of the data is 3D models. Such type of the data can come from many different applications, like some design applications, or, for example, some specific tools which produces very detailed STL files for the 3D printing. Another type of the data can come from the computer-aided engineering applications, where usually it is need to visualize the results of calculation via different graphics, diagrams, or it is sometimes it is need to illustrate the distribution of the calculated parameter over the analyzed body. And finally, Visualize SDK supports point cloud. The next question, which is not less important than the first, is where the Visualize SDK can be used. First of all, it is a computer-aided design applications. Here it can be simple viewers with markup functionality or even full functional editors. Another area is a computer-aided engineering application. Here, Visualize SDK can be used in two different stages. First of all, it is the mesh generators part of the CAD, of the computer-aided engineering application. And the second stage is the post-processing, where it is need to visualize the calculating results. Computer-aided manufacturing and the BIM application are another areas where Visualize SDK also can be successfully used. Certainly, this list is not full, and generally speaking, practically every application which need to draw something can use Visualize SDK. Despite the fact that Visualize SDK is first of all focused on the performance, we're also thinking about the quality of the produced drawing result. And one of the most common techniques how it is possible to produce realistic rendering result is to map the 2D image onto surface and 2D or 3D space. Such procedure called texture mapping. Visualize SDK has an extensive support of the texture mapping, including possibility to assign different textures on the different faces inside the shell, or to use some predefined overmapping techniques like spherical or cylindrical mapping. And certainly, Visualize SDK supports classic way of texture mapping by using the texture coordinates, which can be assigned on the vertices of the shell. Another feature which is provided by Visualize SDK for the visualization quality purpose is the visual style objects. Such object contains a set of properties which influence on the different parts of the rendering process, like, for example, adding the silhouettes to the classic hide and line mode, or implementation of the sketch visual style, which mixed where each edge is drawn with a few pixels. This is an overhang effect. Or when each edge drawn multiple times with a small noise. This is a jitter effect. Another interesting types of visual styles is the X-ray visual style, where all scene is drawing as semi-transparent, and shades of gray, which allows us to drawing all objects in the grayscale mode. Now, when we speak about what can be visualized with the Visualize SDK and where Visualize SDK can be used, it is need to discuss how it should be done. So on the next few slides, I will give a brief description of the Visualize SDK. Initially, Visualize SDK is consisted from 3 blocks. First block was the GIJS API, which allowed to manipulating with devices and views. and allows to load the geometry to the visualize SDK. The second block is the vectorizer block, where many different actions are performed, like geometry simplification or calculating on the inherited attributes. And finally, the last block is the rendition block, which performs the final output. The problem with this architecture is that a client application cannot directly manipulate with the Visualize SDK. And since GI.js API was already discussed many times in the past, further we will focus only on the new simplified Visualize API. This API allows to manipulate with the internal graphics cache. The structure of this cache is very similar to the typical structure of the computer-aided design database. This cache contains a few types of objects. First of all, models and blocks. These objects are geometry containers. They are practically equal, but only the contents of the model can be directly rendered, while the contents of the block can be rendered only after inserting the link to this block to one of the existing model. Another type of the object which is placed in the graphics cache is attributes. Attributes are divided onto two groups. First group is the simple attributes like color or line type scale or transform matrix, which can be defined by one value. And the second type of the attributes is a complex attribute like materials and other objects, which presents a union of simple attributes. And the last two types, devices and views. Devices usually encapsulate the graphical user interface window and owns, updates, and generates the views. Views usually stores the parameters of the camera and many other properties. To draw something with Visualize SDK, first of all, create the device, create the view, and append this view to the device, create a model, fill this model with the geometry, and append the model to the view. The root object of the Visualize SDK graphics cache is the entity, which is a container of the geometric primitives. Geometric primitives are divided into four groups. First group is the 2D primitives like polylines, ellipses, circles, text, and images. The second group is the 3D primitives like shells and meshes. The third group is the complex primitives like polycylinders, NURBS, or grid, which is divided onto simple geometric primitives during the vectorization. And the final group is the miscellaneous geometry primitives like subentities and subinserts. Visualize SDK isn't simply a rendering engine. It also provides a set of useful functionality which can be used by the client application. And first of all, it is the selection and highlighting. Currently, Visualize SDK supports the following 5 modes for the selection. First of all is selection by point. Then it's a selection by polyline or by fence. And finally, it is a selection via rectangle or polygon in 2 modes, full inside and crossing. For the optimization performance, selection procedure based on the spatial tree. Currently is under implementation. We currently implement the possibility to perform subselection, where it will be useful. It will be possible to select geometric primitive inside the entities, and subgeometry selection, where it will be possible to select separate edges and faces inside the shell. And another feature which are currently implemented is the possibility to set up the selection level for the entity, which allow us to speed up the selection process, because in this case we will be able to filter some entities if the selection level is not equal to the selection request level. For the highlighting, Visualize SDK has 3 modes. First mode is a simple selection by color. It is a very useful mode, but sometimes we have a problem with this mode because under this type of highlighting, we cannot recognize the structure of the highlighted body, especially if we will now select all object. Here we are able to see only the green spot with some contour of the initial body. The next type of the highlighting resolves this problem. It's the highlighting via color with transparency. So in this case, we are simply, without any problem, can recognize the structure of the object, and even in the case if we perform selection of the whole object. And the final mode, which are able for the highlighting with Visualize SDK, is highlighting by stipple. Such mode can be useful for the drawings which contains a huge amount of objects with many different colors, because in this case there is possibility when the color of the object will be equal to the color of the highlighting, and in this case it will be very hard to understand is this object already selected or it's simply its own color. So in this case such mode will help. Also, Visualize SDK provides a set of another useful features. First of all, it is a possibility to isolate and hide a piece of geometry, collision detection or clash detection, which allow to analyze the presence of the intersection between different bodies. And well-optimized implementation of such functionality allow to use this option even in real time. And the next feature is the markup. Visualize SDK API are ready for implementation over it of any kind of the markup functionality. For saving and loading data for the internal Visualize SDK graphics cache, Visualize SDK provides the Visualize stream format. The loading and saving and loading data from this format is supported by the Visualize libraries. This is a binary format which allows to load and save the full structure of the internal graphics cache, including all properties of the devices and views. This format supports multi-threading. This format includes lossless data compression, which allow us to make the final file smaller. And finally, this format supports partial loading. Visualize SDK currently support 7 formats for the import. First of all, it is the ODA supported formats like DWG, like DGN, like Revit, and PRC. The next 2 formats are very commonly used for the exchange of the 3D data. It is the STL format and the OBJ format. And finally, Visualize SDK supports Autodesk Point Clouds format. As a natural continuation of the import functionality, we have implemented the feature which we called aggregated database. This feature allowed to mix the data from different formats in one graphics cache or even in one view in one window. And now we will demonstrate to you how it is possible to be done on the small demo. Here we will mix the data from the Revit file, then we will add data from the OBJ file, and finally we will add data from the PRC file. So first of all, we will remove this car and substitute it by the track from the OBJ file. Here it is important to know that certainly here it is need to use additional transform matrix because we should scale, translate, and rotate the data from different files to same size, same position, and same orientation. So now is the final stage. We will add the PRC engine to the back of this track. Now it's possible to see the results, how it's possible to merge the data from different formats in one cache and in one view. The root task from the rendering performance point of view is minimizing the number of calls to the graphic software. And it means that some geometry primitive should be merged with purpose to organize it by common attributes. And now such ability is provided by the new layer, which was added to the rendition block inside the Visualize SDK. This layer called Thin Graphics Manager. This Thin Graphics Manager finds compatible graphic streams and merge them into graphic stream unions. On the next iteration, already graphic stream unions are merged with each other. And the procedure continues until we will have no compatible unions anymore. On the next small demo, we will demonstrate this process in the reality. So first of all, here it is possible to see a large number of yellow rectangles, which represents the initial graphic stream. Now we will start the process, and we are able to see how the streams is unionized to the graphic stream unions, which are marked by the red rectangles. And after that, already unions start to merge with each other. So this is the end. And the final performance increasing, it strongly depends from the structure of the drawing. So the best result we can achieve for the drawing which contains a significant number of objects with the same attributes. If we'll speak about the 3D models case, here again all depends from the drawing's complexity. So the good result we will have in the case if the model contains from the significant number of small parts. Like for example in this case, where the described procedure allows us to reduce the number of GPU calls practically 10 times and allow us to achieve the 4 times optimization. This model will contain about 2 million with half triangles, so it is not too huge model, and formally we should wait a good rendering performance. But as we will see, the situation is different because here we can see only 4 frames per second speed. The problem is that in this file, this 2 million with half triangles is distributed over the huge number of entities. Here we have about 40,000 of entities and 100,000 of shells. So this situation certainly produces a huge amount of GPU calls. Now we again reopen this file with using the new technique. And as you can see, now the performance is very, very good and we have no problem. One of our main goals is to give for our users the possibility to achieve a good feedback from their investments in the hardware. So in the previous slides, we have shown how we load the CPU. So now a few words how we use the modern functionality at the GPU. During last year, we added the support of the geometric shaders for drawing of the silhouettes and line weights. And this allows us to significantly increase the performance for such drawings. So on this demo, now we will switch on the visual style, hidden line visual style with silhouettes in the old mode without using the geometric shaders. And the main part of calculations are now on the CPU side. And you can see that we have not good performance. It's only about 1.5 frames per second. Now we will switch on the using of geometric shaders. And no problem with performance. But here we should mention that that only relatively new graphics cards supports well these geometric shaders. Now we have multi-threaded support in the following areas. First of all, it's loading data from the visualized stream format. The next area is the generation of the geometry. And is it possible to see from the presented table? This multi-threading support allows us to increase the performance from the moment of open the file and till the final drawing result will be on the screen. In both cases, as for the 2D case and as for 3D case, the increasing of the performance are more than 2 times, which is really a good result. And the final area where we now support multi-threading is the import from the DWG, because DWG also supported multi-threading in the loading procedure and in the regeneration, which are also part of the import functionality. So we support multi-threading in the import from DWG. And is it possible to see from the next table? Again, as for the 2D case and the 3D case, we again have significant performance increasing. The main feature of this new tessellation is the tessellation accuracy now depends from the deviation parameter, which in its turn depends from the 2 variables. First variable is the physical size of the pixel, and the second variable is the facet trace parameter. The dependence from the physical pixel size allow us to achieve different tessellation accuracy for different zooms. Certainly, it is very useful because when we are very far from the object, we are not interested in the too-detail tessellation. But certainly, if we are close to the object, we want to see all details. All details should be very smooth. So, in this case, we should use much more detailed tessellation. The facet trace variable allows us to achieve the different tessellation accuracy for the same zoom. Is it possible, for example, for these two images, where the picture are practically identical, but the number of triangles is different practically in 5 times. But on the next picture, we can see the payment for this situation, because certainly in the case when we zoom in to the model, all the parts for the case of less number of triangles are too rough. But it is possible to regenerate this data, and they will be again smooth enough. Under the usability, we first of all understand the presence of the examples, which allow users to study and to understand how it is neat, how it is possible to work with Visualize API. Here we have some very simple, very basic application. It's something like Hello World. This application has 2 options. First option demonstrates how it is possible to create and draw the data from the scratch. And the second option allows to import data from the OBJ and draw it. Another useful resource where it is possible to see the information how to use Visualize SDK is the import modules, especially a module which imports data from the OBJ file. Because here it is possible to find many different examples how to use the Visualize API. And finally, it is our main demonstration, main debug application, Visualize Viewer, which cover practically all Visualize API. So here it is possible to import data from any formats, including certainly Visualize Stream format, to change the properties, of the views, devices, to add some geometry to work with markups and many other functionality. So it is our major and most useful sample. Also, during last year, we will add the .NET part, .NET API for the Visualize SDK. And certainly, we implement the sample application, VPF Visualize Viewer, which also covers a significant part of the .NET API. At the end, I want to give a brief summary and to talk about the future plans. So Visualize SDK is a flexible, ready-to-use visualization engine. We support S2D and 3D data, support text, images, and point clouds. Visualize SDK support TrueType, SHX, and RCS fonts. Visualize SDK is good optimized as for the 3D data and for the 2D data. Visualize SDK has multi-threading support and uses the advanced GPU effects like silhouettes and order-independent transparency. Visualize SDK includes optimized collision detection algorithms and has rich import possibilities. And finally, Visualize SDK has a C++ API and the .NET Languages API. Now about the future plans. And first of all, it's the implementation of the level of detail as for the shells and for the BREPs. And if we'll speak about BREPs, and remember the new tessellation, which was discussed a little bit later, we should add the BREP interface to our Visualize API. The next our goal is to add the collision detection to our Visualize API, because now we support it only on the low-level GI API. The next our goal is to implement the partial loading from the Visualize Stream format and finalizing the sub-entity selection and sub-geometry selection. Also, we want to add the support of the opacity, bump, and reflection maps. And now if you want about more far plans. So first of all, we want to add the cutting planes, cutting section to our Visualize API, because again, such functionality are now able only on the low-level GI API. The next, our goal is to add support of the level of detail for point cloud. Then we plan to add some new customization parameters for the highlight functionality, like, for example, possibility to highlight faces and edges via different colors. And finally, we want to add the shadows and ambient occlusion functionality. At the beginning of the presentation, we have discussed two very important questions. What can be visualized through the Visualize SDK and where it can be used? Now the third important question, where can it be visualized? And on this question, we'll give the answer my colleague, Ilya Zavyalov.
Hi everyone, my name is Ilya Zavyalov, and I want to say more about where it can be used. So, Visualize, among other good features, got another one. It's a presence on all common platforms. So, Visualize can be run on desktop platforms, on mobile and web platforms, and even on virtual reality. We support 56 different platforms overall. And beside that, we support different devices like GL-ES2, OpenGL, DirectX, and GDI. For mobile platforms, we support Android operation system and iOS operation system. For Android operation system, Visualize API available through GNI interfaces, and for iOS through Swift wrappers. For web platform, we support all major browsers like Microsoft Edge, Firefox, Google Chrome, Safari. How we port Visualize on web platform? To do that, we use EM scripting toolset. And right now we provide two versions. It's SMJS version and WebAssembly version. WebAssembly is a new modern format for web application, which provide possibility to run web applications quite fast in browsers. Unfortunately, not all browsers support this format. So for such cases, we provide SMJS version. And here you can see the architecture scheme of our web server, which is hosted on Amazon. So first of all, you can see it's a front-end web server. We use Nginx. It handles all static requests and proxy user requests on the backend web server. This is our application level web server, which handle client requests and work with user files. It stores them on our third instances. It's network file system storage. The same instances is used for cloud services, which we got right now 2 instances who able to open these files and stream geometry data on the client side. Besides that, client application can execute specific requests on such instances. So, what features you got with Visualize? First of all, it's a common API on all platforms. So, if you're already familiar with Visualize API, it will be quite easy for you to write a new application on new platform, or maybe you want to port your existing application on new platform. It will be quite easily. Besides that, you can get very good performance speed. And of course, you can support various formats like DWG, DGN, Revit, OBJ, and so on. And now I want to show you our demo sample. Let's open. some file. It's a DWG file with engine paths. So right here you can see that it's opening quite fast. You can perform different operations like pan, zoom, rotate, and even you can switch visual styles right here on client side. Let's open another file. Let's open a Revit file. So here you can see the model with house. We can switch camera position, and made the same tools as well, the same operations on this file. And I want to show you that we able to open the files with point clouds. So you can see this model, this tree with a lot of points. It's quite performance, and you're able to open it and view. And here I want to show our next demo. We named it a sandbox because you can see that on left side there is an online code editor, and on right side you can see the result of such code. So here we just download file, open it, switch visual style, and with few lines of code add simple animation. So you can see it's quite easily and quite fast. Let's open the next sample. It's actually the previous sample, but with additional modification. So here we can open the same file, isolate some specific object, and here you can add additional information about this object. And let's open the next sample. It's more about automation. You can automate some routine tasks, or maybe you can create some templates right here quite easily. Here we create small template which actually can be downloaded from this sample, and it can be opened in desktop application. Thank you all.